Imagine you are holding a brand new vehicle key in your hand. Behind that moment is a hidden world of years of grueling tests and data-driven decisions. Every vehicle tells a story, and durability is the chapter where it either shines or fails. This video reveals the engineering process that ensures your car doesn't just work, it lasts. From RLDA to corrosion, every mile driven is simulated before the first customer turns the ignition. From sun-scorched deserts to freezing tundras, and from city potholes to high-speed driving on mountain roads, every mile a vehicle travels is a test in disguise. That's why durability testing is one of the most vital aspects of vehicle development. We're not just testing metal, we're safeguarding lives, reputations, and billions in warranty costs. In this video journey, we'll take you behind the scenes of a full durability validation program. Vehicle durability is the most critical and essential part of a vehicle development program. My name is Tom Resch, and I'm going to take you through the journey of vehicle durability testing and test profile development. So buckle up and let's get started with RLDA. A test vehicle is outfitted with a suite of precision sensors, strain gauges on suspension arms, accelerometers on chassis and body, wheel force transducers capturing 6 degrees of freedom, forces and moments at every corner. All this data is collected through high-speed data loggers, synchronized with GPS and vehicle CAN signals. We record how the vehicle behaves through potholes, turns, stops, climbs, and more. These measurements are essential. They don't just show us what happened, they help us predict what will happen. By analyzing stress magnitudes, frequencies, and event sequences, we build fatigue life models, validate finite element simulations, and generate test cycles that mirror actual usage. With RLDA data in hand, we are now ready to replicate real-world damage on purpose. Proven ground test surfaces are designed and built to replicate the harshest driving conditions that can be encountered around the globe. So get ready, this is going to be a bumpy ride. Let's jump into proven ground test surfaces. Paved high-speed circuits, evaluating stability, handling, and tire wear at sustained high speeds. Cobblestone and Belgian block roads deliver high amplitude, low frequency vibrations, ideal for challenging suspension durability, interior component stability, and triggering squeaks and rattles. Potholes courses impose sharp vertical impacts to stress suspension and wheels. Corrugated tracks excite resonance and fatigue in mounts, brackets, and joints. It also assesses suspension durability, chassis stiffness, and comfort on deteriorated roads. Off-road tracks evaluate chassis robustness, suspension travel, and drivetrain resilience in rugged conditions. Twist tracks induce torsional load into the chassis and body in white. Gravel roads simulate stone chipping, dust ingress, chassis resilience, suspension integrity, underbody protection against debris, and body abrasion. Mud and water surfaces are used to challenge sealant effectiveness, drivetrain protection, and contamination resistance. Ice, snow, loose sand, and other low-mu surfaces apply stress on powertrain systems. Each surface is selected and sequenced based on RLDA frequency data, ensuring we accelerate the most relevant failure modes. Durability testing is performed at multiple levels. Simulated durability testing involves advanced methodologies designed to accurately and efficiently replicate real-world conditions that products will encounter throughout their life cycle. This testing is critical in ensuring reliability, longevity, and compliance with stringent standards and specifications. Durability testing is performed at multiple levels. Vehicle durability testing is critical for assessing reliability longevity, and compliance to the most stringent of standards and specifications. So let's go ahead and shake, rattle, and roll our way into types of durability tests.
Multi-axis shaker rigs are pivotal in durability testing, enabling simultaneous excitation along multiple degrees of freedom, including vertical, lateral, and longitudinal axes. These rigs precisely reproduce dynamic load profiles derived from field data, ensuring accurate replication of complex vibration scenarios such as road-induced loads in automotive applications or turbulence effects in aerospace. Modern shaker rigs incorporate sophisticated closed-loop control systems, accelerometers, and force transducers to dynamically adjust input signals, ensuring precise fidelity to measured conditions. Environmental chambers play a crucial role by replicating the diverse environmental conditions that products may encounter, including temperature extremes, humidity fluctuations, thermal cycling, corrosion, dust, and water ingress. Precise environmental simulation is achieved using programmable climate chambers, capable of rapid temperature transitions, humidity controls, salt spray exposures, water pressures, and ultraviolet radiation cycles. Coupling these chambers with shaker rigs or test benches enables simultaneous environmental and mechanical stresses, thereby accelerating failure mode identification, shortening development timelines, and significantly enhancing product reliability and durability. Together, these test methodologies and equipment ensure highly accurate, accelerated, and repeatable durability simulations, enabling engineers to confidently assess product robustness and optimize designs to withstand demanding operational conditions. At the component level, test rigs apply real-life load histories to isolate parts. At the component level, test rigs apply real-life load histories to isolate parts, such as control arms, mounts, or subframes, and other vehicle components. This allows accelerated testing, failure detection, and design refinements with repeatability. Additionally, powertrain durability tests are performed at the e-axle and vehicle level to assess the durability of powertrain systems under a multitude of loads, environments, and use cases. Full vehicle testing, by contrast, validates how systems interact under dynamic conditions. Vehicles are run 24/7 on multiple surfaces, with each loop replicating years of wear. Squeak and rattle teams monitor NVH. Chassis teams analyze crack initiation growth. Together, these tests recreate what vehicles endure during their lifetime of global use.
In reality, many failures do not come from one stressor, but many combined stresses acting together. Let's go ahead and jump into combined environmental and mechanical testing and how these methodologies are used to drive out real-world failures.
In combined testing, we first expose vehicles or components to salt spray, which simulates coastal humidity or road salt in winter climates. Then, without cleaning or repairing corrosion damage, we run the same vehicles on a durability track. Why? Corrosion weakens welds, degrades coatings, and allows rust jacking, creating stress risers that accelerate fatigue. For example, a frame rail weakened by salt may crack under twist loads. A bolt with galvanic corrosion may shear during impact. By testing both together, we discover failure paths that would not appear in isolation or separate tests.
Once all data is captured, the real engineering work begins.
We apply digital filters to clean up noise, then break the data into events, such as pothole hits, curb strikes, or resonance cycles. Then we use rain flow counting to identify load reversals, categorizing fatigue cycles by magnitude and mean load. With this, we apply Miner's Rule, a damage accumulation method that predicts fatigue life based on the number and severity of each load cycle. We apply the damage equivalence factor using Miner's Rule to calculate cumulative fatigue damage. The equation for this is D equals the summation of small n sub I over capital N sub I.
Where D is the cumulative damage, small n sub I is the number of cycles experienced at load level I. Capital N sub I, which is the number of cycles to failure at load level I. This is from fatigue testing, or an S and N curve.
Let's go ahead and run through an example using this equation.
First, let's define the equation with some more context. Minor's rule, also called Palmgren minor linear damage rule, is a cumulative damage model used in fatigue analysis. It estimates the total damage D that a material experiences under varying stress levels, and failure is assumed to occur when the summation is greater than or equal to 1. Imagine you're trying to figure out how much life is left in a part or system after it's been through different types of stress. You know, the part has experienced a mix of light, medium, and heavy loads, and you want to estimate how close it is to failing from fatigue. Let's now walk through that process to see how Minor's rule works. Let's now look at the data table, that is the load history, which is broken into 3 levels. The first is load level 1, which is low stress. The part went through 15,000 light load cycles. From past testing, we know this part can survive 80,000 of those light cycles before failing, so we've used up about 18.75% of the life for this type of load. Next up is load level 2, which shows an example of medium stress. The part experienced 25,000 medium load cycles. It can also survive 80,000 of these before failing. That means we've used up 31.25% of the life at this level. Finally is load level 3, which is a high stress. The part went through 10,000 heavy load cycles. It can only take 40,000 of these before it fails. So this used 25% of the life at the high load level. Let's add this all up now. To estimate the total fatigue life used, we add up the percentages from each load level. 18.75% for the low load, plus 31.25% for the medium load, plus 25% for the high load. When you total that, you get 75% of the fatigue life used. The final result tells us that the part has used 3/4 of its fatigue life. That means it's still safe to use, but only 25% of its life is left before it's expected to fail from fatigue. If you're planning ahead, now's a good time to consider replacing it or redesigning it for a longer life, depending on the type of component or part and its application. So how engineers use Minor's rule in the real world? It's used in vehicle durability testing. Engineers use this to check if parts can last a full vehicle life, say 150,000 miles or 10 years, under real-world loads collected from RLDA. It's used in accelerated lab testing. With accelerated testing, instead of waiting years, engineers run tests using harsher, faster loading to simulate years of driving. Then, they calculate how much fatigue life that represents. It is used in design validation. Multiple design options are tested, and engineers calculate the fatigue damage for each. The part with the lowest fatigue damage, in other words, the one that uses the least life, is usually the better design. Minor's rule offers a simple yet powerful way to predict fatigue life. By summing damage from different stress levels, engineers can make informed decisions about part reliability, maintenance timing, and design improvements, ensuring durability, safety, and performance over time.
The final product of all of this work is a comprehensive durability test profile.
The highlights of durability test profile development process include collecting customer usage data to establish realistic usage profiles, utilized load spectrum analysis to quantify component stress and strain under typical conditions, accelerated test cycles by increasing stress, frequency, and load while preserving realistic damage modes, and determining equivalent mileage through empirical correlation. This empirical correlation can be expressed as cycle subtest is equal to mileage subtarget over mileage sub per cycle times the correlation subfactor, where mileage subtarget is the total distance in miles or kilometers that the vehicle or component must be validated against to simulate its expected life. And mileage sub per cycle, which is defined as the distance simulated or covered during a single durability test cycle. And the correlation subfactor, which is a multiplier used to account for different severities, real world versus test conditions, or environment to test lab translation. It helps bridge the gap between test conditions and actual usage conditions. It accelerates or adjusts the number of cycles needed based on how well the test correlates with field conditions. Let's go ahead and run through some examples of different correlation factor values. The first is proving grounds with mixed surfaces. This has a high real-world match and has a correlation factor typically of 1. It is a good 1-to-1 match to actual field conditions. The next is laboratory rig tests with controlled stress profiles. This has a moderate real-world match and often has a correlation factor of 1.3. Lab conditions are slightly less severe than proving ground conditions. Accelerated track testing on extreme surfaces has a very high real-world match and has a correlation factor of 0.8. This test is more aggressive than actual field usage. Simulation only or FEA models have a low real-world match and use a correlation factor of 1.5 to 2.0. Lower correlation due to lack of real wear mechanisms, but this is a good start to get an initial idea and eradicate any low-hanging fruit in durability issues with your vehicle design. Desert durability testing for global vehicles. As far as a real-world match, this depends on the region, and the correlation factor can be between 1.2 and 1.6. It is adjusted to reflect localized harshness. The correlation factor is often derived from historical field data comparisons, failure mode analysis, and real-world telemetry, such as with collecting canned data, and engineering judgment and experience. Let's go ahead and run through an example now using the empirical correlation equation.
In this example, our goal is to simulate 150,000 miles of real-world usage. Each test cycle on our rig represents 500 miles, and based on how well the test environment matches actual field conditions, we apply a correlation factor of 1.3. This factor adjusts for the fact that lab conditions may not perfectly mirror real-world wear and tear. First, we divide the total target mileage by the mileage simulated per test cycle. The solution of the division problem is 300 test cycles would equal 150,000 miles if the test conditions perfectly matched reality. But since the test setup is slightly less severe than the real world, we multiply this by 1.3. After solving, we get a product of 390 test cycles, which are needed to properly replicate the effects of 150,000 miles of real-world driving. This accounts for the difference in severity between the lab and field environments. Therefore, to replicate 150,000 miles of durability life in this example, we would need to run 390 cycles of this simulated testing. The end result of these post-processing and test profile development activities may look something like the following example. In this example, the final test profile outlines the following based on how each surface is weighted by how often it occurs in real driving for this example vehicle program. We might assign 20% of a cycle to cobblestones, 30% to rough asphalt, 10% to potholes, and include humidity chambers and salt baths between loops. Finally, we validate the cycle. We run pilot vehicles, monitor damage, and refine the profile if the results don't match our real-world benchmarks. The result is a test cycle that gives automakers confidence before a single car leaves the assembly line.
Durability testing is the science of prediction, the art of acceleration, and the foundation of trust.
We've seen how RLDA captures real-world data, how proving grounds simulate global roads, how corrosion and vibration work together to degrade components, and how data post-processing gives engineers the power to forecast failure. All of this culminates in one outcome: a test profile that reflects reality, compressed, repeatable, and precise.
And this is how modern engineering ensures that every vehicle, every truck, every SUV can go the distance. Thank you for watching this video. I really hope you enjoyed that. And if you have any questions or comments, feel free to reach out to me at the link below for my website. If you need help with developing test strategies for activities such as vehicle durability, feel free to reach out to me as well. I also have training, courses, and other content on my website, so don't forget to check that out. Thanks again for watching, and have a great day.